All right, welcome back, class. This is going to be our third lecture. We're going to be talking about the need of the muscles in your body to utilize oxygen and how they get oxygen from your environment. A couple quick notes before I get into this lecture is I just wanted to say, specifically for an online class, there's not a lot of interaction between me, the instructor, and you, the students. So really, this is going to be really student driven by you guys if you guys want your questions answered, right? If you want to send me emails, if you want to have Zooms with me, I would love to sit there and talk through concepts in more detail or explain them in different ways than I am during lectures, right? I can only do so much recording myself and trying to explain to you the complex concepts of what are occurring in exercise. And there's only so much I can do, right? I'm trying to do my best. I'm trying to go through it at a relative pace where you guys aren't sitting there for 2 hours. Also, try not to go through it too fast. Those of you who have physiology as a background, if you've taken a physiology course before, some of this is probably a lot of review for you. And those of you who have never taken a physiology course before, maybe only taken anatomy, this might be a lot of new stuff for you. So I'm trying to find this middle ground for everyone. So if you feel like you're falling behind, make sure you let me know when you're telling me, hey, I need this answer, I need this answered. I would love to help you out, right? I would love to sit down with you or meet with you over Zoom or whatever it might be and talk about the things that you were not understanding. Like I said in my first introductory lecture, is that these are all concepts I think are going to be very, very important for you going forward, right? And I want to give you the best opportunity to learn these things. I want to do my best to make sure that you are understanding what we're talking about so that you can apply these concepts going forward to whatever work you're doing so that you can be the best at what you're trying to do, right? So basically, the summary of that is if you have questions, please, please, please reach out to me. I can't get verbal feedback from looking at your face in a class to know whether or not I'm talking too fast or you're understanding it at all. So that's going to be entirely up to you guys. Okay, so please reach out to me. But what we're going to do now is we're going to jump into our next lecture here. So I'm going to share my screen with you guys once again. And we'll jump into the lecture. Okay, so muscles need oxygen, right? Title of this chapter. We're going to talk about what that really means. Okay, so jumping in. So air pressure, right? We should all know air pressure, right? Or relatively what air pressure is. The composition of air is the same at elevation. So the air, the atmosphere that you breathe, right? People say, well, like, what's the most predominant gas in the atmosphere? A lot of people will say oxygen. It's not true at all, actually. Nitrogen composes about 78% of the atmospheric air. We just don't use nitrogen and our lungs don't react with the nitrogen and we don't use it, right? Only about 20% of the air that we breathe in is oxygen. Now, if you go up to the top of Mount Everest or you go to sea level, you go to Death Valley, the composition of the air is going to be the same 78%, 21% oxygen, nitrogen, and then carbon dioxide and other gases, and any moisture that's in the air as well, right? The relative amount of these particles, right, is be due to the relative air pressure at these elevations is due to the amount of these particles. So at Mount Everest, there's a lot less total air particles, which means less air pressure, right? So it's harder to breathe, right? There's not like there's less oxygen in terms of percentage, there's less total oxygen particles, and therefore it's harder to breathe up there. At so elevation, there's less pressure, so less air volume moves into the lungs. So what actually occurs when you breathe is your diaphragm here will contract, like you see right there. Diaphragm contracts, relax, contract. That expands the volume of the lungs. If we remember, I believe Boyle's law, right? Pressure one, volume one equals pressure two, volume two, right? If you increase the volume of something, you are decreasing the pressure within it. So if we increase the volume of these lungs by pulling on it, like it is there, pulling on it with the diaphragm, we're increasing the volume, which is going to draw the air into the lungs. If you ever use like a turkey baster, right? If you squeeze the turkey baster, stick it in water or in the gravy or whatever it is and release it, right? You're allowing the volume of that turkey baster to expand. It's getting bigger, which creates a negative pressure inside the baster, a negative pressure inside the lungs, like we're seeing here, right? And that's what draws the air into it, right? So if there's a, so in the breathing cycle, right? the relaxation of the lungs pushes the air out, just like a balloon. If you let a balloon go, the elastic recoil of the balloon is the same as it is for the lungs. The elastic recoil is what pushes the air out. And then in the case of your lungs, the diaphragm contracting is what opens the lungs and draws the air in, right? So what essentially we need to do is we need to get the pressure of the lungs to be less than that of the atmosphere, which causes the atmospheric air to flow into the lungs. And that's how we inhale. We're not going to talk too much about the interpulmonary pressure and transpulmonary pressure. Essentially, just know that this diaphragm is not attached directly to the lungs. So essentially, it pulls, which pulls on this sac, this pulmonary sac, which pulls open the lungs, right? And this kind of just goes in a cycle, just like the breathing cycle, that allows us to open up the lungs, okay? Oxygen to the blood. So the oxygen, when it's brought into the lungs, moves into the alveoli, right? Moves into the alveoli, which then diffuses across these alveoli into the bloodstream. So we see here the pulmonary capillaries around this alveoli, right? It's deoxygenated. It's diffusing into the capillaries there. And then we have the oxygen or the oxygenated blood, right? So the oxygen, when it enters the blood, immediately moves to red blood cells, which are the transfer devices for oxygen, right? We should know that, right? Red blood cells are how you transfer oxygen throughout the body, right? And red blood cells have these protein groups called hemoglobin, right? There's a hemoglobin right here. It comprised of a protein structure as well as iron. That's why iron is really, really important for blood-related issues, right? So the oxygen moves in, it diffuses into the bloodstream, which then moves to a red blood cell and binds to the hemoglobin onto the iron group. So anemia, right? In this case, anemia is when you don't have enough red blood cells, right? Which would be a problem because if you don't have enough red blood cells, you don't have the capacity to carry oxygen, and then you can't get oxygen to the working tissue that need it, right? So CO2 also functions this way. So when you produce CO2 in the muscle, right? Remember when we talked about the Krebs cycle, we're producing CO2 in the Krebs cycle in the electron transport chain. That is brought back to the lungs also via the hemoglobin. It comes back to the lungs, it's released, and then it flows out when you breathe out, right? So CO2 moves from the blood across the basement membrane into the alveoli, and then that is exhaled, right? So diffusion is what's occurring. Both oxygen and carbon dioxide are moving down their concentration gradients. They're diffusing, in the case of oxygen, from the alveoli into the bloodstream, and in the case of carbon dioxide, from the bloodstream into the alveoli, right? So anemia is iron deficiency. And for you ladies in this class, you're probably very familiar with anemia, right? Most women go through a menstrual cycle once per month or once every 28 days. During that period, as I'm sure we're all well aware, you lose a pretty sizable portion of blood, right? And in that portion of blood, you are losing a lot of iron. That's why most one-a-days for women contain iron and one-a-days for men do not, because men, as we know, do not have that monthly blood loss that causes this disruption or this decrease in iron in the body. This is also why women tend to bruise more easily, because women are generally more iron deficient, because iron is not necessarily an easy thing to get in the diet, right? You're eating a lot of red meats, right? You are probably getting enough diet or enough iron. But again, I would say that the consumption of red meat is probably more highly associated with men than it is with women. And red meat is a very concentrated source of iron, right? Spinach is another good one. Dark leafy greens are good ones. But meat is generally the best place to get it, right? So, so in developing nations, like parasitic infections and lack of diverse diet are main reasons for iron deficiency, right? In the developed world, right, women lose it mostly through blood loss. Okay, that's what we're talking about here. As well as for children, because you are rapidly growing and you need a rapid increase in the red blood cells needed to carry the oxygen around your rapidly growing body, you need to have a higher iron diet, right? So if you have these iron deficiencies as well, you'll see it manifests as poor energy status. You'll see compromised reproductive function. You'll see impaired bone health. You'll have fatigue. You'll have all these things seen here. So anemia is a very important condition that we don't generally see in the first world that we live in right now. But in developing nations, it can be very important because they're lacking it in terms of diet, as well as lacking proper nutrition, nutritional information and the abundance of high iron foods, and therefore we will see high incidences of anemia. Now, looking at normal red blood cells versus sickle cells, right? I'm sure we are all heard of sickle cell anemia. What that is it's a genetic mutation that causes the red blood cell to be shaped like a sickle like this, instead of the sickle here, instead of like a biconcave or a donut-shaped red blood cell, right? We see here this red blood cell has a biconcave look. It caves right here, and it caves right here, perfect for holding oxygen. Now, sickle cells don't really have that. They're kind of just like a bent C shape, like a crescent moon, right? And they are not as efficient at transferring oxygen. So people who have sickle cell anemia usually have a harder time being really prominent athletes here, right? Now, we're wondering why have sickle cell? And specifically, why is it so concentrated in Africa, right? Why is it so concentrated in Africa and India? Well, those who have malaria, that is actually a genetic mutation that was beneficial to prevent you from malaria infections, right? So we know that malaria is very prevalent on the African and the South Asian continent, right? So people over the years or over generations developed sickle cell anemia, right? Or sickle cells to prevent against the spread of malaria, right? So causes cells to die early instead of a 90-day to 120 days. So cells will die in about 10 to 20 days instead of 90 to 100 days, which helps to stop the spread of malaria, right? It limits it limits the ability of these individuals to carry oxygen to different places, right? So people who were or had sickle cell anemia probably weren't the best hunters and probably weren't the best long distance travelers because they lack the ability to transfer oxygen to the working muscle that many other people could, as well as you struggle a lot during intense exercise because you can't transfer that oxygen, right? So blood to the muscles, right? Oxygenated blood is transported to the muscles via arteries, right? So we talk about the difference between veins and arteries. Some of you probably already know what it is, right? But arteries carry oxygenated blood. Not always, right? Arteries are anything that move away from the heart, okay? Most of the time, arteries will carry oxygenated blood, yes, but arteries are just any sort of vessel that moves blood away from the heart. Veins will move blood towards the heart. Now, for the most part, everywhere in the body, arteries are carrying oxygenated blood, except for where? Except for the pulmonary circuit. When the heart pumps deoxygenated blood from the heart to the lungs, that is where arteries carry deoxygenated blood, goes into the lungs, gets reoxygenated, and comes back to the heart via the pulmonary veins. Those are the veins that have oxygenated blood. Otherwise, throughout the systemic circuit, throughout the rest of the body, arteries will generally carry oxygenated blood, yes. But important to remember that distinction. So again, much like oxygen moving across the alveoli by diffusion, oxygen diffuses across the capillary into the muscle, right, to be used in the electron transport chain for internal respiration, right? And then CO2 moves from the muscle into the capillary. So we see that over here, right? We see oxygen flowing from the blood into the muscles, right? And we see carbon dioxide flowing from the muscle into the bloodstream. And that makes sense. There's a high concentration of oxygen in the bloodstream. So when it gets to a muscle cell that does not have very much oxygen, it's going to diffuse into the muscle cell, right? And carbon dioxide, which is produced in the muscle cells via the electron transport chain, right, in the Krebs cycle, is going to be pumped out. It's going to have a higher concentration here. It's going to move out through diffusion into the bloodstream to be carried back to the lungs, right? So oxygen delivery, right, can improve with training, right? We can improve our cardiac output. We can improve AVO2 difference, which means that we can essentially make our muscles more efficient at extracting oxygen from the bloodstream. So if they're more efficient at extracting oxygen from the bloodstream, that means that the oxygen that's arriving there is more useful, as well as we have higher blood volumes, right? If we have higher blood volumes, it means we can carry more oxygen. More oxygen means more ability to get that oxygen into the tissue, right? So we remember that these are both occurring by diffusion, right? Both occurring by diffusion, but they are just kind of occurring in the opposite manner. All right, so right? We look at this here, right? Essentially what we're looking at is partial pressure. So partial pressure of oxygen here, partial pressure of carbon dioxide here. And again, you don't need to know these numbers perfectly, right? But you do need to know, right? You do need to know what the general basis of what's going on here is, right? So when the blood is leaving the alveoli, when it's leaving the lungs, right, it has a very high partial pressure of oxygen. And you can think of partial pressure as just basically total amount, right? So we could say there's like 100-fold particles versus 40-fold particles, right? It's pumped back to the heart, right? And then it goes to the muscles, right? Again, here, pumped to the heart, goes to the muscles. When it's on its way to the muscles, it's still holding on to that oxygen, right? It hasn't gotten to anything that's extracting the oxygen from the bloodstream yet. When it gets into the muscles here, we see the oxygen then moves into the muscles, right? And the carbon dioxide moves into the bloodstream. Now, once it leaves the muscles, we see that the partial pressure of oxygen has gone down and the partial pressure of carbon dioxide has increased, right? And these numbers specifically, you don't have to remember because these change, right? As you can imagine, if you are working more strenuously and the muscle is utilizing more oxygen, this number is going to be lower, right? If you are barely working at all, if you're just sitting there and you're watching, you're watching the NFL playoffs, you're watching, the Georgia Bulldogs pull it off against Ohio State here in the last weekend, right? If you're sitting there, this partial pressure of oxygen is going to be much higher because you're not actually extracting it in the muscles. The muscles don't need it, so they're not using it, right? Same with the partial pressure of carbon dioxide. If you're not working hard, you're not producing carbon dioxide, this partial pressure of carbon dioxide leaving the muscle isn't going to be as high, right? And then we see it come back through the right atrium into the right ventricle, right? And then that's pumped to the pulmonary, pumped via the pulmonary artery into the lungs, leaves the pulmonary loop here via the pulmonary vein, back to the left atrium, left ventricle, and then into the systemic circuit, right? So you should know this blood flow. You should know that blood is oxygenated as it moves into the left atrium, into the left ventricle, and then around the systemic circuit, and then it returns to the right atrium of the heart via the superior and inferior vena cava, right, into the right ventricle and into the pulmonary circuit. So you should know this general process, and you should know what's happening to the relative levels of oxygen and carbon dioxide, okay? On to the next. So aerobic capacity, right? So we're going to talk about a few different functions and fundamental properties of aerobic capacity, right? So the ability of the muscles to use oxygen received from the heart and lungs to produce energy, right? So aerobic capacity is just the ability of you to produce energy from the oxygen that's been pumped around your bloodstream, right? So VO2 max, right? VO2 max is a term that you will hear a lot in this class and probably other classes, and you might have already heard me say. It is the maximal rate of oxygen consumption. It is the maximal ability of your muscle cells to consume oxygen, okay? Now remember, oxygen consumption is not the same as oxygen inhalation, right? You can sit here and breathe, you can go and breathe in a lot really, really fast and hyperventilate. That's not changing the amount of oxygen that's being consumed by your muscles. What does change the amount of oxygen consumed by your muscles? Exercise, right? That is what causes your body to consume more oxygen. And because you're consuming more oxygen during exercise, what happens to your ventilations, to your respirations? Well, they increase, right? They increase because you need to provide more oxygen to those working muscles because they are consuming more muscles, or they're consuming more oxygen, right? So V means volume per time, O is oxygen, max is the maximum you can utilize maximum you can utilize for your whole body, right? Or per kilogram usually. So the Fick equation is very important because the Fick equation is our measurement of blood flow. Now, the measurement of blood flow, the two factors that contribute to blood flow are going to be stroke volume, SV here, stroke volume, that's the SV, and heart rate, HR, right? So stroke volume is the amount of blood that can be ejected out of the heart per contraction, and heart rate is exactly what it sounds like, the amount of beats per second. So if your heart rate's 80, it's going to be beats per minute. So if the heart rate's 80, you're beating your heart 80 times per minute. Stroke volume is the volume of blood that is ejected out of the heart during each contraction, right? So there's a few different things here, right? Heart rate times stroke volume times AV difference, AV oxygen difference. right? So we can look at VO2, right, by knowing the difference in oxygen and carbon dioxide in the blood returning to the heart, as well as if we know the heart rate and the stroke volume. So you can know the absolute value for VO2 max. What is the absolute amount of oxygen that you were consuming at any one point during exercise or rest? Or the relative, which is usually used more often because it is based on the kilogram, right? If you are a larger individual, let's say I have a 400-pound individual sitting next to me here, okay? They are larger, and if they contain more muscle mass, their absolute VO2 is going to be higher just because they have more metabolic tissue, they have more muscles, they require more oxygen just to be alive, right? But if I am more aerobically trained, or let's say there's someone who's even more aerobically trained than me, right? They might be lighter and they might be smaller and their absolute VO2 might be less, but the ability of individual muscle cells to utilize that oxygen and turn it into energy might be higher. So they can consume oxygen more efficiently, right? So people who have a higher training status usually have higher relative VO2s because the mechanisms that supply oxygen to the working muscle and the mechanisms that utilize that oxygen are much more highly developed, which allows them to produce more energy, right? And then finally, we have a MET here, a metabolic equivalent, right? So 1 MET is essentially the amount of energy that you burn at rest. So if you're doing something at 2 METs, you're doing something that requires 2 times as much energy as you would at rest, right? So on and so forth. If it's 10.5 METs, that's 10.5 times as much energy being utilized as what you would be using at rest, right? And again, here we see our RER, right? We see our RER, volume of CO2 over volume of O2. And as we should remember, if this is closer to 0.7, right, that is what? We're utilizing what? Fats, right? Should be fats. Can't really type with this, I apologize. And as it's closer to 1, it's closer to 1.0, that is carbs, right? I apologize, really hard to draw. This is good enough. You guys get the gist, right? I'm not going to spend all day on that. You guys get the gist, even though that looks terrible. All right. So stroke volume and Q is intensity increases, right? So Q, remember, Q is blood flow, right? This is just total blood flow, the amount of blood that's flowing through the heart and through the body, okay? As you begin to get closer to your VO2 max, your maximal pace, right? Stroke volume begins to plateau. Stroke volume begins to plateau. Now, this changes with different populations, but for the basis of this class, we're going to say the stroke volume is mainly plateauing at about 110 to 120 milliliters per beat. Meanwhile, right? Meanwhile, cardiac output continues to go up, right? Cardiac output's going up. So what's happening? What's happening? How can stroke volume plateau, but our cardiac output is keeps on going up, right? Well, we have one more factor, if you remember, right? Heart rate. Heart rate continues to go up throughout exercise. Now, you'll eventually get to your peak and you'll kind of plateau. For the most part, heart rate continues to increase until you get to maximal exercise. So even though stroke volume is providing the initial boost to cardiac output, once it begins to plateau, that increase in the heart rate is what's actually providing higher cardiac output, right? And that's why when you exercise, your heart beats harder, right? You need to pump more blood throughout the body, right? So your heart beats harder, right? It also beats more forcefully, more force per contraction, which means higher stroke volume. But eventually that stroke volume is plateaued out and you rely on the increase in heart rate to keep on increasing your cardiac output, okay? So we see here with different populations, right? We see heart rate, right? In elite populations, right? It can go, or we see stroke volume at certain heart rates, right? So in elite populations at, let's say, 110 heart rate, right? We have a higher stroke volume for elite individuals. As we get more intense, as we get closer to 160, 180, which is what most people's heart rate max is, you see here elite individuals are more able to pump out more blood per stroke volume or per stroke, right? So the stroke volume continues to increase versus trained or untrained people, as well as your cardiac output. Again, as you would imagine, those who exercise more can pump more blood around their body because the mechanisms that allow them to pump more blood around their body are more efficiently created and fine-tuned, okay? Then here we see our speed versus our VO2, right? So as you continue to increase in workload, right? As you continue to increase in workload in speed, eventually your VO2, the amount of oxygen you are consuming is going to keep going up, 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 and then it'll plateau. And that will be what your VO2, that is what your VO2 max is. If you were pre-training, if you haven't gone through any training yet, you keep on running faster, 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 and faster and faster. And eventually you get to a pace where your ability to consume oxygen is maxed out. Your ceiling is hit. You can no longer consume any more oxygen, and you have to maintain that pace, and eventually you'll peter out and you'll tire out, right? Versus after training, post-training, you see that individuals, right, as they continue in speed, increase in speed, they can go past that plateau. They get a higher ability to consume oxygen, right? The alveoli, right? They're getting better at diffusing oxygen across into the bloodstream. More importantly, right? More importantly, there's more red blood cells, and red blood cells themselves are more efficient in transferring oxygen to the working muscle, as well as the working muscle is more efficient in using that oxygen, right? So all those factors play into VO2 max, right? The fusion, the movement of the oxygen from the lungs into the working tissue utilizing that oxygen itself, they all play large factors, specifically the movement, right? The red blood cells moving that oxygen to the tissue, right? So VO2 can be predicted from submaximal testing as well. So essentially we see here, delete that, no, I stayed. Sorry, y'all, I don't know what's going on here. I don't know why that's staying there. Give me 1 second here. Oh, there we go. Okay, so we see here, right, that heart rate and VO2, excuse me, heart rate and watts, right, have essentially a pretty linear relationship, right? These things are pretty linear. As you work harder, as you're working at a higher power output, more watts, right, your heart rate is relatively linear, okay? So if we go back, right, we see here, let me see this, right, cardiac output, right, is very closely tied to work rate, okay? And so for individual A here, right, individual A who is more trained, right, at any given work output, their heart rate is slower, right? So it will take them longer to reach their heart rate max than an untrained person would. And therefore, right, they can work at a higher cadence at their heart rate max than somebody who is untrained, right? This untrained person at any given work rate needs a higher heartbeat to maintain that work rate. So at 150 watts, they have to have a beat of 150 or 145 instead of 130, right? They have a higher heart rate at any given work output. So when they get to their heart rate max, right, their work output is going to be lower than a trained person, right, who is more efficient in utilizing the cardiac output mechanisms to provide oxygen to the muscles, right? You can use this to predict VO2 max, right? This is a way, obviously it's not as accurate as running an actual VO2 max test, but it is a way to measure that, right? So lactate threshold, this is something we talked about in the first lecture a little bit, talking about lactate and lactic acid and acidosis, right? So lactate threshold, the first threshold here is the point at which lactate begins to increase. Now I'm going to preface this and I'm going to say this a lot, right? The more important thing occurring here is the acidosis that's accumulating, right? The reason that we say lactate threshold instead of acidosis is because lactate is a large carbon molecule, right? It's a carbon chain, three carbons ion with hydrogen ions. Acidosis is just one free-floating hydrogen ion. So back in the day when we were first initially discovering what was occurring here, we just noticed that lactate was going up and we thought, okay, if lactate goes up, they feel more tired. Lactate must be the cause. That makes sense, right? But actually, the acidosis that is occurring at the same time as the lactate production is what is predominantly causing the fatigue, right? Just back in the day, we did not have the mechanisms or we didn't have the technology to measure that. So this distinction was lost over time, right? And people tended to say lactic acid now, when in reality, we should be talking about acidosis, right? Because the lactate itself, if you remember back to our food as fuel lecture, right? Lactate itself can be utilized as a fuel, can be turned back into glucose and utilized again to make ATP, right? So, and this happens predominantly because of our increased utilization of anaerobic energy systems, right? The anaerobic energy system, glycolysis, is what is producing pyruvate very, very rapidly, right? It's producing pyruvate too rapidly, essentially. Remember, our glycolysis produces pyruvate to move into the electron transport chain, right? Produces pyruvate to move into the electron transport chain, as we see here, right? Essentially, what is happening is if this glycolysis is producing, this glycolysis is happening too fast, right? The electron transport chain and Krebs cycle can't handle all that pyruvate, right? So that pyruvate gets converted into lactate and acidosis, right? So if there's too much, if glycolysis is occurring too fast, the Krebs cycle and electron transport chain can't handle it. That means that the acidosis and lactate buildup is going to be rather extreme, and it's going to cause you to begin to fatigue, right? And then we also have the onset of blood lactate accumulation, right? It's the OBLA, right? So this is a second threshold. So this production is faster than clearance, right? So essentially what this is saying is that up to this point, right, we're getting a lot of lactate accumulation, but our clearing ability of it, our buffering systems, the way that we get rid of this acidosis and lactate, are able to handle that. Now at OBLA, right, at the second threshold, the production is much faster than the clearance. So the acidosis begins to accumulate, lactate begins to accumulate, right? So when these things begin to accumulate, we begin to fatigue, right? So we want to make sure, right, if you're an exerciser and you want to run for as long as you can, you want to stay below this, because once you get above this, you begin to fatigue very rapidly. You're almost going straight up here, right? Right? You get to have a lot of blood lactate, which means a lot of acidosis, okay? So it's very, very important for long distance runners to know their lactate threshold so that they can stay just below it so that they don't produce this excess amount of lactate and acidosis and don't fatigue too rapidly, right? So we're saying here corresponds to ventilatory threshold. We'll talk about that a little bit later in the chapter and in the year as well, right? Further explains lactate threshold is just a proxy measure for the real inhibitor of the exercise free hydrogen ions, right? Like I said, lactate is good. Lactate can be used as a fuel source and is responsible for buffering acidosis, okay? Lactate threshold, right? So the first threshold, right, it begins to increase. Again, this little bit of review, right? And then the second threshold, this is a repiece pretty much on that same slide, right? The second threshold is the one where we really begin to have a problem, right? We really begin to struggle. And what this is just showing is that with training, right, you can increase speed or power for a while before you begin to have that lactate threshold happen, right? So before you have that incidence, that spike of lactate, you can be working at a faster pace or a harder pace than if you were, let's say, untrained here, okay? This second threshold is what corresponds to ventilatory threshold. So we see here, right, we see blood lactate on a athlete 2, athlete 1. What we see here is that athlete 2 is hitting their lactate threshold much later. Therefore, they are a more well-trained individual. So for this case, right, running speed, this athlete could run at probably like 11.7 miles per hour and stay just below their lactate threshold and perform, right, perform better because they are running at a faster pace. Athlete 1 is only running at 9.9 miles per hour. Athlete 2 is running at 11.7 miles per hour, right? Last time I checked, the faster you run, the quicker you get done with the race, right? So if they're both staying just below the lactate threshold, athlete 2 will win this race. In order for athlete 1 to get to that same race pace, to get to 11.7, they have to be producing a lot more lactate and a lot more acidosis, which is going to cause them to fatigue more quickly, right? Same thing we're seeing here in terms of time, right? They're riding a specific pace. Athlete 1, right, is in the middle here. Athlete 3 in the bottom. Athlete 2, again, is the most aerobically inclined, right? They are the most aerobically fit. Excuse me, I'm saying that backwards, right? Athlete 3 is the most aerobically fit here, right? This is blood lactate over here. So at the 40-minute mark, right, athlete 3 has a much lower blood lactate level than athlete 1 and 2. Therefore, you'd be looking at this and saying athlete 3 is the most aerobically fit. I apologize for that confusion there, right? But we see here athlete 2 has much higher blood lactates at any given time during the race, which means they're going to feel more fatigued and fatigue faster during that race. Right, so resting heart rate, right? We talk about resting heart rate, right? 220 minus your age or 208 minus 0.7 your age, right? They're going to come out to somewhat close measures, right? Usually this 208 minus 0.7 of your age is the best one to use. This is the one that I'm going to say that you should probably use. I'm going to say that you should use that one just because it's generally the most accurate. Right? 220 minus your age is a little old, but you can really use either one because it's going to vary pretty widely for individuals. As well as tachycardia is a resting heart rate over 100, so that means a fast heart rate. Bradycardia is a resting heart rate under 60 beats per minute, right? Tachycardia over 100, bradycardia under 60. So we see the effect of endurance training on parameters of aerobic fitness, right? So again, we see here, right? We see post-training, pre-training, post-training, pre-training, right? We see these dark boxes for each one of these things, right? Lactate and then heart rate, right? For heart rate here, we see at any given running speed, their heart rate is lower. And also as well for the blood lactate at any given running speed, their blood lactate is lower, right? So what we're saying is that the body is not only getting more efficient, right? You don't need to boost the heart rate as much because stroke volume is getting better, but you also are producing less lactate, which means less fatigue is manifesting, right? And like I said, producing less lactate, but more importantly, producing less acidosis, which means less fatigue is manifesting, right? So resting heart rate and health, right? So resting heart rate is a good indication of cardiovascular disease mortality, right? So those who have lower resting heart rate tend to be more predisposed to living a longer, healthier life. Those who have higher resting heart rates, right, it is a sign that is indicative of cardiovascular disease or poor aerobic health. So if you have a low resting heart rate, right, you usually are healthier. And if you have a higher resting heart rate, you usually are less healthy. So the course I just took, we took a cardiovascular physiology course with Dr. Freddie here in university. We took a EKG and a resting heart rate. My resting heart rate came out to 49 beats per minute, which I was very, very pleased with because I do not think I'm aerobically fit at all. I hardly do cardio, maybe 10 minutes each time I work out, probably closer to like 5 minutes each time I work out, and I hated it a lot. So hopefully that's a good indication for me for living a long, healthy life. However, I do tend to make a lot of stupid decisions. So maybe, maybe those will balance out, but who knows? Who knows? Based on my heart rate, though, you would think I'll be doing okay. But as you see from this graph too, cardiovascular disease is much higher in men than it is in women, right? As we know this, men have a higher prevalence of cardiovascular disease, right? So even at the same relative resting heart rate, individuals that are male versus female tend to have higher cardiovascular disease mortality rates. So we're talking about the control of the heart, right? Extrinsic control of the heart. So we have parasympathetic and sympathetic neurons that attach to the SA node, right? So the SA node, the sinoatrial node, is the node that initiates the heart rhythm that you have at any point. So the rhythm that your heart beats at any one point, right? The SA node is saying either be at this pace, or this pace, okay? Sympathetic, as we should remember, is your fight or flight, right? Parasympathetic is your rest or digest. And you can think of parasympathetic as like a parachute, slowing things down. Sympathetic is your fight or flight. So as you would think, the parasympathetic slows down your heart rate and the sympathetic neuron increases your heart rate, okay? And what you actually see here is that the baseline for the SA node, the default setting for the SA node is at 100 beats per minute, right? So you at your resting heart rate of, let's say 60, right, or mine of about 50, right, my resting heart rate of about 50, I actually have vagal tone. The vagus nerve, which is the parasympathetic nerve right here, is actually stimulating the SA node to contract less often, to depolarize less often. So as you get faster, right, you get pull, or the vagal node becomes less active, or the vagal tone becomes less active. And then once you hit 100, now the sympathetic nervous system begins to stimulate the sinoatrial node or the SA node to beat faster, right? So we see here, we can see a few different things, right? We see the effect of beta blockers in exercise, right? Propranolol will decrease the heart rates. It'll increase your stroke volume, right? These are all compensatory reactions. Essentially what's happening here is because it's decreasing heart rate, you see that stroke index needs to go up. And you see that pulmonary pressure needs to go up. And this isn't super important. It's kind of showing what these beta blockers can do to you. And essentially what I'm looking for here is for you to understand that heart rate response can be altered and mitigated depending on certain drugs and depending on the exercise that you're putting it through. So not only does exercise alter heart rate, also drugs alter heart rate, specifically beta blockers or cardiac enhancers, right? These are things that people use during open heart surgeries, during specific diseases, right, to help individuals who may have cardiovascular disease issues. Right, so we see here, right, as well on medication, right, certain medications can boost heart rate at certain exercises, right? So at any given exercise intensity, right, certain medications can also boost heart rate, like we just said. So O2 deficit and and excess post-exercise consumption, right? Your EPOC, excess post-exercise consumption, right? So we see here as you begin to exercise, as you start exercise, right? You jump to whatever it is. Let's say you start sprinting, okay? Your oxygen consumption jumps, okay? Your ability to provide oxygen does not jump as fast as just you beginning exercise, right? So when you take off sprinting, right? When you take off sprinting, your ability to provide oxygen to the body or to the muscles is not as fast as your decision to just start sprinting, right? So you get this O2 deficit, this deficit between the amount of oxygen your body actually requires, the amount of oxygen you are able to produce to it. It takes a little bit of time to ramp up the processes, to ramp up heart rate, to ramp up stroke volume, to provide oxygen to those working muscles, right? So you get this deficit here. Now, after exercise, right, even after you rested, after you completely stopped, right, you have this EPOC, your excess post-exercise oxygen consumption. And this is essentially saying that after exercise, even though you weren't working as hard anymore, you not only need to refill these oxygen reserves and refill the oxygen saturation of the red blood cells and the muscles themselves, right, but also, right, the processes of recovery from whatever you just did also require oxygen. So even though you stopped working out, EPOC, right, this excess post-exercise oxygen consumption is essentially the amount of oxygen that you need to recovery from that exercise, right? So when you stop exercise, oxygen consumption metabolic rate remains elevated. As you should know, when you stop sprinting, if you run a 100-meter dash and you stop sprinting, you don't just stop breathing as hard, right? Generally, you realize how much harder you are breathing, right? That's that post-exercise oxygen consumption manifesting in real time that you probably noticed before. Right, and then ventilation during exercise, as you guys have all probably noticed, right? When you are not working out very hard or you're walking pretty slowly, right? Your pulmonary ventilation, how often you breathe, is pretty low, right? Very, very light exercise. You may be breathing 40 times a minute, right? Maybe, right? If you're at a moderate, right, you may be breathing up to 80 times a minute, and then super, super heavy, right? You're up to maybe 120 breaths per minute. Or liters per minute, excuse me, not breaths per minute, liters per minute, right? In terms of breaths as well, right? As you begin to exercise very lightly, you breathe a little bit more, right? And if you exercise more heavily, you breathe a lot more in terms of both volume and amount of breaths, right? I'm sure you've experienced this. As you begin to work out harder, you begin to breathe more and more forcefully. Right, so which condition, right? Which condition will have higher energy expenditure during exercise, during EPOC? So we're looking at high intensity interval training for 4 minutes intervals at 95% peak heart rate. Your sprint interval training, 6 30-second Wingate sprints separated by 4 minutes, or our slow sustained 30-minute pace at 80% peak heart rate. And what we see here essentially is it's saying that the net oxygen consumption for this steady exercise is actually higher, right? It's actually higher. But for the high intensity interval training and the 6 30-second Wingate training, we see a lot more EPOC, right? And that's probably due primarily to the fact that these are highly anaerobic exercises. This is more aerobic. So during the actual exercise, we get more oxygen consumption because it's actually aerobic, versus these are more anaerobic. So you have a little bit less oxygen consumption because it is not requiring as much oxygen because it's relying more on the anaerobic mechanisms. But afterwards, the recovery from these exercises, right, actually requires more oxygen than the sustained one, okay? The thing to be seen here, though, is you look at this and you go, okay, well, that means that I'm utilizing more energy or utilizing more oxygen during sustained running, right? Sustained running. So that's what I should be doing. I should be doing sustained running to utilize more oxygen. The thing to keep in mind here is that you have 4 4-minute intervals, right? 4 4-minute intervals. So you're really only working out for 16 minutes here, but you're getting relatively close to the same amount of overall oxygen consumption, about 55 to 70. It's a little bit lower, but even this one specifically, right, are 6 30-second Wingate sprints separated by 4 minutes of active recovery, right? You're only working for 3 minutes here, right? You're working for 3 minutes compared to 30 minutes, and you're getting almost the same amount of oxygen consumption, right? So this is why sometimes you see long distance runners go through bouts of high intensity interval training like this, 6 30-second Wingates with 4 minutes rest, because you can get a lot more adaptation to the cardiovascular system, right, in a short period of time than if you're doing sustained running. Now, sustained running is still the best way to provide adaptations for sustained running. this is just another way to kind of quote shock the system, right? It's another way to initiate a stimulus or a stressor to the system so that you can go through adaptation. This is more information on that if you want to read more about that. So we're talking about ventilation and energy metabolisms, right? So ventilation matches metabolic rate. As you work harder, right, you are burning or utilizing more ATP, right? Which means you need more oxygen for the ATP, right? The stimulus is the activity. You want to run, you want to sprint. So let's say you go for a run, right? The oxygen, right, needs to be brought into the muscle tissues because the muscle tissues are utilizing ATP, right? And the muscle tissues have increased their amount of ATP that they need, right? Which means they need more oxygen. So your exercise is what's stimulating the increase in the intake of exercise, right? So as you begin to exercise more quickly and more forcefully, you need to breathe in more oxygen, right? Right? And then we're talking about ventilatory threshold here as well. So ventilatory threshold is a concept that is very hard for me to explain. I don't know if I'm bad at explaining it or it's just a tough concept. I tend to have students that struggle with this every single year in my lectures, right? So we'll slow this down for a second. This is not a complex question. This is meant for you to overthink. You're sitting there right now listening to me talk, right? Probably bored. You're probably sick of listening to me talk, right? But why are you breathing, right? Just think about this. Why are you breathing right now? And we talked about it throughout this lecture. What are you breathing for, right? You're breathing to get oxygen, okay? Your body is forcing you to breathe because the metabolic tissues, specifically the muscles and other organs in your body, need that oxygen to produce ATP, right? So your body is breathing because you need oxygen, right? That's the default state. Body breathes because it needs oxygen. At some point here, right, as you exercise more quickly, you begin to ventilate more quickly. We talked about that. More strenuous exercise means more, which means more ventilations. At some point here, though, you're going to reach a threshold at which you are going to ventilate disproportionately to your oxygen consumption. The amount of ventilations that you have is going to become uncoupled or unlinked to your oxygen consumption and instead become linked to the need to remove acidosis from the body, right? So you can remove acidosis from the body, right? You see lactic acid getting really, really high here. You can remove acidosis from the body by ventilating more quickly because ventilation drives out CO2, right? Which helps you to mitigate acidosis, right? So the point of what ventilatory threshold is now your breathing is not increasing because the exercise is increasing, but it's increasing because you have this rampant acidosis in your body, right? So to review this, at this point, your body is breathing in response to the oxygen demand of the body, right? As oxygen demand goes up, breathing or ventilation goes up. At the ventilatory threshold now, the stimulus of acidosis in the body is so strong, so dangerous to your activity per se, right? That you're going to ventilate even more quickly than you would have, right? If you were to continue this pace, you would have been ventilating like this. But because of this ventilatory threshold, right? Or at this point, at this ventilatory threshold, ventilation is increasing disproportionately, right? We see this greater spike right here, right? We see a bigger increase than you would normally see. And this bigger increase is because you are trying to remove acidosis from the body, right? So you're sitting there right now, you are breathing because you need oxygen. As you begin to work more forcefully, you begin to breathe more rapidly because you need more oxygen. At the ventilatory threshold, right, you begin to increase ventilation even more rapidly than you need to, because you need to remove the acidosis from the body. I know this is really hard to think about because everyone always thinks that you're just breathing for oxygen, right? But remember, once you get to this threshold, once you get to this certain really extreme moment, you're breathing because you need to remove acidosis. Now, remember, if you're breathing in out, right, you can't breathe exhalation without inhalation or inhalation without exhalation. So now you're breathing even faster, right? You're breathing more and more and more, even faster than you need to. You're just breathing in more oxygen than you need, right? Which, if you remember from my other lecture where I said oxygen consumption, or earlier in this lecture, oxygen consumption does not mean oxygen inhalation, and vice versa. This is a case where that's true, right? You are now ventilating in even more oxygen than you need, right? So you are maximizing the ability to ventilate and oxygen, but your muscles are still consuming it at the same rate, right? Just like I said, if you sit here and you breathe really rapidly, it's not changing oxygen consumption, right? Once you get past the ventilatory threshold, right, you are now breathing to remove acidosis from the body. A side product of that, a byproduct of that, is that yes, you are now breathing fast enough to get the oxygen that you need, but the ventilation is now driven by the lactic acid or acidosis rather than by the oxygen demand. Now, I hope I covered that in a way that you can understand, right? If you have questions about that, please feel free to reach out to me. I know that I have a hard time explaining this, or I know this is a hard concept. Like I said, my classes always struggle with this one. So please feel free to ask questions on this if you have any, right? So ventilatory threshold point where it increases, there's an increase in ventilatory equivalent, right? What we talked about, RER increases. It's associated with lactate threshold and partial pressure of carbon dioxide, which makes sense, right? As acidosis increases, right, ventilation increases because you're working harder, right? If you're working harder, you're producing more acidosis, you're ventilating more. At some point, you get to your ventilatory threshold, where you're ventilating even more rapidly than your oxygen consumption requires, right? To mitigate the acidosis by breathing out carbon dioxide. So look at this. Is ventilation the limiting factor in exercise? I can talk about VO2 max, right? I talked about the diffusion of oxygen across the alveoli, right, into the bloodstream, and then the bloodstream moving that to the actual working muscles, right? Is the ventilation, is the breathing the rate limiting step? No, in most cases, right? Unless you have like COPD or you have some sort of pulmonary issue, right? Respiratory muscles count for 10% of VCO2, 50% of Q during heavy exercise. Respiratory muscles are very fatigue resistant, right? Greater oxidative enzymes, mitochondrial density, and capillaries than many other skeletal muscles, right? So the diffusion of air across the alveoli into the bloodstream, as well as the muscles that drive inhalation, are not the rate limiting step of oxygen utilization. Really what it is, right, is the red blood cells delivering the oxygen, right? Even the muscle cells themselves can create plenty of mitochondria and oxidative enzymes to utilize that oxygen. The primary rate limiting step for aerobic exercise is usually red blood cells and the hemoglobin in those red blood cells, right? And this is why blood doping is a thing, right? If you're familiar with what blood doping is, a lot of cyclists do this. What essentially you are doing is if you're not familiar with blood doping, is you take blood out of you months before the race. You concentrate that blood down into your red blood cells to get rid of the plasma, and then you pump that blood back into you right before your race so that you have a higher concentration of red blood cells than you normally would. And because you have the higher concentration of red blood cells than you normally would, you have a greater ability to transfer that oxygen to the working muscles, which means that you're going to perform at a higher capacity and you're going to cycle faster, you're going to bike faster during your race. So summary, right? I threw a lot at you there with oxygen, carbon dioxide, ventilatory threshold, right? Composition of air is the same in every elevation, right? But air pressure decreases at higher altitudes, resulting in less volume being breathed in, right? Because there are less total particles at higher elevations, right? That means less is being breathed in during your exercise, right? Oxygen consumption, oxygen moves from the alveoli across the membrane into the blood, right? You should know where oxygen is moving across, right? You should know the basis of where it's going and what it's used for, right? It's used in the muscle, right? Red blood cells are packed with millions of hemoglobin molecules, each of which can transport 4 O2 molecules, right? So each individual hemoglobin, which there are millions of within the red blood cells, can transport 4 oxygen molecules, as well as it can transport 4 carbon dioxide molecules, right? Because it binds to the 4 iron molecules, which within each one of those hemoglobins, right? The Fick equation is very important, right? VO2, right, is going to be our blood flow, right, times AV oxygen difference, right? As well as remember our cardiac output. The 2 factors for cardiac output are stroke volume times heart rate. Heart rate increases linear with intensity, right? So as you exercise more quickly, heart rate increases. But remember, stroke volume begins to plateau, right? So stroke volume plateaus, but heart rate continues to increase. Lactate threshold, right? Talk about lactate threshold. First point, lactate begins to increase. Specifically, remember, we're talking about the acidosis. The acidosis is what's important. That is what was providing the limitation to your exercise, right? You need to buffer and mitigate the acidosis in order to prevent fatigue, right? That is what's primarily causing the fatigue. The lactate is not the problem, okay? Ventilatory threshold is the point at which the amount of air breathed increases disproportionately to the oxygen consumed, right? Usually the breathing, your ventilation is driven by oxygen consumption, right? At ventilatory threshold, you begin to breathe even more quickly than you need, right? Even more quickly than the oxygen consumption because you need to buffer that acidosis, right? Parasympathetic input decreases heart rate, sympathetic input increases heart rate, right? Rest and digest versus fight or flight. The oxygen deficit that occurs at the beginning of exercise and the excess post-exercise oxygen consumption that happens after exercise are features of oxygen consumption, right? Those are things that occur when you begin to do exercise, right? And then typically the limiting factor for O2 delivery is the red blood cells, right? O2 delivery is a limiting factor, not the red blood cell, or excuse me, not the ventilation and not the muscles themselves. It is the ability of the body to actually transport that oxygen, which is what the limiting factor is. That is what prevents you from performing even higher, hence why blood doping is a thing. So that's the end of our lecture here today. Again, as always, if you guys have any questions, make sure you guys reach out to me, please. Make sure you guys ask whatever you want. Make sure we're getting those readings done. Make sure that you guys are posting 3 quality comments on each one, right? I'm sure this is the point of the semester where people are going to start to get lazy about it. Okay, those comments are automatically graded. Okay, so if they're not giving quality material, they're not giving quality content, you're going to begin to lose points in those things. And they're very, very easy points, right? It takes you probably 30 seconds to think of something to say, right? It's a very, very easy way to get it. At this point too, right, please check in with me if you feel like you're falling way behind in the course, or you feel like the course is too easy so far. Please let me know. I'll make some changes. As well as always, if you have questions, please reach out to me. I would love to talk to you. Other than that, hope you guys are having a good one, having a good semester, and I will see you guys next time.